Okay, so now we can start. This is hopefully you can see the screen, and also hopefully you can hear me. Can someone confirm?
Yes, we can see and hear your voice as well.
Thank you. So today we shall be talking about the congruence of integers. That's the topic for today. Another way, you could also call it modular arithmetic instead of congruence of integers, but they both mean the same thing. We'll call them congruence of integers for today. So we will start with what is usually known as the division algorithm. So the division algorithm says the following, that if a and m are two integers and m is a positive integer, so we don't care what a is, but m must be positive, then there exists a two unique integers q and r, such that 0 would be less than or equal to r and strictly less than m, such that a is equal to mq plus r. So the key word here is unique. So let's try to unpack that. So unique, this r and the q will be unique provided this condition is satisfied. If this condition is not satisfied, then the value of q and r may not be unique for any pair a and m. So by this restriction guarantees that the value of q and r are unique. You can't find more than one pair of values at work. So the q is called the quotient, r is called the remainder, and observe also that we have made that special mention that the remainder cannot exceed the divisor m. So here is some example to illustrate this. We will not prove anything today. We are just applying most of these things. We shall not do any proofs. So the only thing we shall do is test the theorem and make note of the fact that q and r must be unique, and that r must lie between 0, can be equal to 0, but cannot exceed m. Now, a is equal to 30. If a is 13 and m is 5, then using this setup, we can write 13 as 2 times 5, which is 10, plus 3. So you could also write 2 times 4, so that you get 8, but now you'd have to add 5, and the remainder will be, times 4 is what, 8. Then you'll have to add, so the remainder now will be equal to 5, which is important for us. Something is not making sense. Yeah. The remainder to be less than 5, strictly less than 5. So the remainder, if we no, this is, we're working with 13 and 5. So the one that maybe can change is this. So maybe what you can do is change 1 times 5 to get 5, but then you'd have to add 8 to get 13, and 8 is much bigger than 5. So that gives us a problem. It doesn't satisfy our requirement that the remainder cannot exceed the divisor. So we must stick to those conditions if you want q and r to be unique. So here is another example where a is negative and m is equal to 3. Then we can, using the same ideas, we can write minus 11 as 3 times negative 4 plus 1. So one might be tempted here to write as 3 times negative 3 to get negative 9. But then that would be a problem, because then you would have to have a negative remainder. To get negative 11, you have to have it as negative 9 minus 2. So the remainder will be negative, and we want the remainder to be bigger than 0. You can see R must be bigger than 0. So you can't use -3 here because it gives you that problem. Similarly, you can't use -5 because then you get -15. And for you to come back to 11 or to -11, you have to add 4.
Yeah.
And now we have a problem because 4 is bigger than our divisor. Someone is need to keep microphone off.
God, now this temptation, no.
Ogutu, Owino, please put off your microphone. Yes, thank you. So keep this in mind. We might use it at some point. So the other thing we need to define is what do we mean by congruence of integers? Suppose A, B, and M are integers, and we again insist that M is positive. Then we can say that A is congruent to B modulo M if a difference of A and B is divisible by M or is a multiple of M, where K is also an integer. So basically what we mean is if A minus B is divisible by M, then we can make the same statement that A is congruent to B modulo M. I think there should be some examples coming up. So the other way to look at it is that if A is congruent to B modulo M, then A and B will have the same remainder when divided by M. We can prove all this, but I think for now we just take the statements as they are. So the the notation for this is if A is congruent to B modulo M, the notation for that is you have A and then you have 3 parallel lines. A is congruent to B, and then you have the modulo M. So that's the notation. So this is what we mean, how we write A is congruent to B modulo M, to mean the difference A minus B is divisible by M. So just that's the definition of congruence of integers. You define that for a pair of integers. So any pair of integers will be congruent modulo M, where M is positive, a positive integer, if a difference of the two integers is divisible by M. Okay. So far, if you have any questions somewhere in between, you can simply put on your mic and ask. Or if you want anything clarified, you just put on your mic and ask again. So here is some example to illustrate this. So we can see that 12 is congruent to 5 modulo 7, because if you subtract 12 minus 5, you get 7, and 7 is divisible by 7. So 12 is definitely congruent to 5 modulo 7 based on our definition. Also, we can make the claim that -15 is congruent to 7 modulo 2, because the difference, -15 minus 7 is equal to, I think there should be a negative here, should be equal to -22, which is the same as 2 times -11. I think there's should be 2 times -11. So the difference, -15 minus 7, can be written as a multiple of 2, and therefore -15 is congruent to 7 modulo 2. So hopefully there is no problem with that so far. Some of this may be already familiar, but take note of what we are doing, because it shall come in handy. We shall be using this in some of the examples.
Okay, I have a question.
Yes.
Okay, I can see -22. That's -15 plus -7.
We are subtracting. We are A minus B. So it's just negative 15 as A.
Yeah, it should be negative 22.
Yes, yes, we made that correction when during the talk. That should
Okay,
be
thank
negative.
you.
And this should be negative 11. So I have just removed the, I'd done the same when I was covering the example. Okay. So I think I'll have to correct the slide later, but in the recording, since I have written by hand, it should be possible to, it should be okay for the recording. Now, here are some properties of congruence. So the first one says if A is congruent to B modulo M and B is congruent to C modulo M, then it follows that A must be congruent to C modulo M. So there's a transitive property. These are we have B here and B here. So these two are different, A and C, but M is the same in both congruences. So under these circumstances, if we know these two statements to be true, then the third one will also be true. A will be congruent to C modulo M. So the assumption here is that A, B, C, and M are integers. M is a positive integer. The next property says the following. If we have these two congruences, A is congruent to B modulo M, and C is congruent to D modulo M, then you can always add the same sides of the congruences. So I can add A plus C. I still end up with a correct statement that A plus C is congruent to B plus D modulo M. I can also subtract the same sides of the congruence. So A minus C is congruent to B minus D modulo M. So this will always work. And then I can multiply also the same side of the congruences. So A times C will be congruent to B times D modulo M. So this third property, or rather this property, the one I'm outlining here, leads to the next one. So if A is congruent to B mod M, you can keep multiplying, raising each side to a power, and you still end up with a correct congruence. That follows from this, right? Because basically you are assuming both congruences are the same. A is congruent to B mod M as one of your congruences. And then again, repeats the same one. A is congruent to B as the second congruence. Both of them should be modulo M, right? So you keep multiplying. I can multiply. If I do it once, I would have A squared will be congruent to B squared. So I can repeat this on and on until I get to my desired power, so that A raised to N will be congruent to B raised to N modulo M. So what this means again is that the remainder when A raised to N is divided by M is the same as the remainder when B raised to N is divided by M, as long as A is congruent to B modulo M. Okay. So the next one is if I have AC is congruent to BC modulo M, and the greatest common divisor of C and M is equal to 1, then I can cancel the C, and I have A is congruent to B modulo M. This can only work if the GCD of C and M is equal to 1. If the GCD is different from 1, you cannot do this cancellation. But if it is, then you can. So you don't lose anything by dropping the C if the GCD of C and M is equal to 1. Well, I mean, basically you lose the C, but you don't lose the congruence. The congruence is preserved. They will still be congruent to C modulo M. Is that making sense so far?
Oh, yes.
Okay. So now we want to see how we can apply some of these properties in certain problems that appear in Olympiad. So here is one trick. If you want to find the last k digits of a positive integer, we'll have the following trick. So if you just want to find the last digit, that's the units digit, it's simply the remainder when the integer is divided by 10, right? So when you divide a number by 10, the remainder will give you the last digit, the units digit. If you divide by 100, it will give you the last two digits. The remainder will be the last two digits, and so on. So if you divide by 10 raised to k, the remainder will give you the last k digits of the number. I believe this makes sense. Okay, I'll clear that. This can be, okay, we'll see this. It can be illustrated by expressing a number as a linear combination of powers of 10. But let's see what happens in next. But so this one is just when you want to find the last k digits of a positive integer. So many times you may be asked to find what are the last two digits of a given integer. So maybe the best, your strategy might be to find out what the remainder is when divided by 100. If you are just finding the last digit of a given number, maybe the strategy that would work would be to try to find the remainder when divided by 10, and so on. That may be worth considering. Okay. Now the units digit, how we're now going to focus on the units digit of a positive integer and how it occurs. So this one says if p, let p be the units digit of a positive integer a, and let n be a positive integer. Right? So p is just the units digit of the positive integer a, and n is any positive integer. So the units digit of a raised to n will be determined by the units digit of p raised to n. So if you know the units digit of a, if you want to find the units digit of a raised to n, you just need to focus on the units digit of p raised to n. So for instance, if I have a number like let's say 2, 4, 1, if I want to find, say, the units digits of 241 raised to 4, I just need to focus on the units digit of 1 raised to 4. If I find the units digit of 1 raised to 4, it will be the same as the units digit of 241 raised to 4. Or if this was 5, if I have 475, it has units digit 5. If I want to find the units digit of 475 raised to 100, for instance, I just need to find the units digit of 5 raised to 100. So the units, these two numbers will have the same units digit. That's what this statement says, or the two statements claim. Now, if the units digit is one of these, if it's either 0, 1, 5, or 6, then p raised to n has the same units digit as p. So basically what it means is that if you have 1 raised to n, the units digit of 1 raised to n will be 1. The units digit of 5 raised to n will be 5. And also this units digit of 6 raised to n will also be 6. So it will be exactly the same. If this is the last unit digit, then Pn will have exactly the same units digit. Again, I will skip the details. I just need that to make sense. So here we have considered the case where the units digit is either 0, 1, 5, or 6. So if the units digit is 4, 9, Then the sequence of the unit digits for p raised to n will be periodic with a period 2. So for instance, if you have 4 squared, you will get 16, right? What about 4 cubed? You get 64. So this keeps going on. If I get 4 raised to 4, what will I get? I think that will be 256, and so on. So you can see what is happening. The units digit is alternating. It's when you consider just 4, the number itself, the units digit is 4. The next one, after squaring, the units digit is 6. After squaring, you go back to 4 again, and so on. So it goes in this pattern. The units digit keeps. So when you have an even power, the units digit is 6. If you have an odd power, the units digit is 4. It alternates. I hope that makes sense. So it repeats after every 2 numbers. So that's what we mean repeats with a period of 2. The same idea can be extended. So we have considered the cases where the units digit is either 0, 1, 5, or 6. Now, the next case we have considered when it is 4 or 9. We still haven't considered all the possible units digit. So these are the remaining ones, 2, 3, 7, or 8. Here, the sequence of units digit for p raised to n is periodic with a period of 4. So if you use 2, for instance, as an example, you can start with 2. That's a units digit. If you raise it to, if you square it, the units digit is 4. If you get the cube, the units digit is 8. 2, if you raise it to 4, the units digit is 6. That is for 16. And then it starts afresh again. It repeats after every 4. So this is how the units digit will alternate. If any of the units digits, if the units digit of our number is any of these 4 numbers. So this characterizes all the possible cases where for the units digit, and it can allow you to study the units digit depending on the last digit of a number. The units digit of the power of a number depending on the last digit of that number. Is it making sense? Or have you all taken off? Are there any questions? We'll soon be doing some examples. So here it is. Here's an example. I think that would be more interesting than the theory. So here we consider some special cases. If the last two digits of, here we just look for the last two digits of any power of 5, a power greater than 2. And the last 2 digits will always be 25. And the last 2 digits of 6 raised to n will follow this pattern, 36, 96, 76, 56, and repeat again. So as you go through the powers, so this would be for 6 squared, 6 cubed will have 96, 6 power 4 will have 76 at the last 2 digits, and I think 6 raised to 5 will have 56 as the last 2 digits. Now 6 raised to 6 will take you back to 36 again, and so on. And then the last 2 digits will continue in that pattern as you get powers of, as you go through the powers of 6. The same ideas can be used for 7. The last 2 digits will be 07, 49, 43, 01, then you go back to 07 and so on. So they repeat after every 4, and that's the pattern they will take. And the last 2 digits of 76 raised to any power will always be 76. All these can be shown in more detail, but for today, we just want to see how they can be used in solving problems. If you don't use them, you just keep them in mind, and you may encounter situations where you can apply them. So here is an example which says the following. When a 3-digit number is divided by any of the integers 2, 3, 4, 5, or 7, the remainders are all 1. So it's a 3-digit number. If I divide it by 2, the remainder is 1. If I divide it by 3, the remainder is 1, and so on. If I divide it by 7, the remainder is 1. So the question is, find the minimum and maximum values of such 3-digit numbers. So what is the smallest 3-digit number, which when divided by any of these numbers will give me remainder 1? And also what is the largest 3-digit number, which when divided by any of these will give me remainder 1? So I hope you have read the question properly, or and understood it as well. If any questions, you can ask. If not, we proceed. So let's see what we do. Now we want to find a number which leaves remainder 1 when divided by any of these 5 integers. So we can find the LCM of this, and it turns out to be 420. So this number is divisible by any of these. So but the number we are looking for should be a multiple of this least common multiple of these 5 numbers plus 1. The remainder is 1, right? The number we are looking for is this x, and when divided by any of these numbers, the remainder will be 1. So basically, you are looking for a number such that x minus 1 would be a multiple of 420. So x minus 1 must be divisible by any one of these 5 numbers. Or if you like, you can say x is congruent to 1 modulo 2. Also, x is congruent to 1 modulo 3, and so on. X is congruent to 1 modulo 4, etc. Hopefully that makes sense. So if you want to find the smallest number, you just keep varying the values of k. So the smallest possible value of k you can consider is 1, and that will give you 420 plus 1. So 421 gives you the smallest possible number that is divisible by all the 3, or rather that leaves remainder 1 when divided by any of these 5 numbers. So we can now change the value of k to 2, because all the numbers we are looking for will take this form. So by just changing the number of the value of k, we get values that satisfy the desired property. Now, if we set k to be 2, this will be 840 plus 1. So the next number would be 841. Now, remember, we were looking for a 3-digit number. So we can't go beyond 2. If we set this to 3, then we will have a number which is bigger than 3 digits. So we only have 421 and 841 as the 3-digit numbers. 421 will be the smallest, and 841 will be the largest one that satisfies the given properties. That makes sense?
Yes.
Good, thank you. So the next question here is, it says the following. It is known that the integers 27, 26, 44, 72, 50, 54, and 64, 12 have the same remainder when they are divided by some 2-digit natural number m. So we need to find the value of m. So the only property there are some properties we know. M must be a two-digit number, and it leaves the same remainder when you divide any of these 4 numbers by this 2-digit number. It leaves the same remainder. Those are the properties we need to carry with us to the solution. So hopefully you have read it so that I can move to the solution. If you have any ideas on how to solve it before we go to the solution, you're also welcome to share the ideas. So I will go to the solution. So since each of the numbers leave the same remainder when divided by m, then any pair of numbers you pick will be congruent modulo m. Any pair of number you pick from our set of, I think there were 4 numbers, will be congruent modulo m. So their difference must be divisible by m, right? That's the definition of congruence. So if you pick the first pair, m must divide the difference because the numbers are congruent modulo m. The difference between this pair gives you 1746. Now 1746 can be factorized as follows. So this will help you find the two-digit factors that we are looking for. Also here we have the difference. This difference is also divisible by m. So m divides 582. So we do the same for the last one again. The difference between these two, and it will be divisible by m as seen here. But we factorize each of them. 582 will be 2 times 3 times 97. And 1358 will be 2 times 7 times 97. So these are all prime numbers. Now we need a two-digit number, which is a factor for all of them. If you look, you see that 97 is the only two-digit number that is a common factor. Any other two-digit number that divides one of them will not be a common factor. So for instance, 2 times 7 will give you 14. 14 is a two-digit number. It's a factor of these two numbers, but it is not a factor of the other pairs, any of the other pairs. Any of the other 3 remaining numbers, it's not a factor. So it's not common. It's a two-digit divisor, but it's not common. For this case, only 97 is a two-digit. Here, if you are looking at 9 times 2, it will give you 18, another two-digit factor, but 18 is not common. We need one that divides all of them. So the only one that works is 97. And therefore, the number we are looking for is 97. Does that make sense? Are we together? Okay, so I will move to the next example. So the next example says, find the smallest positive integer n that lies between 1,000 and 1,100, such that this sum is divisible by 10. So let's see how. So we set up this number as n, the sum of these powers. We set it up as n. Now we can get the last digit. The last digit of this sum will be the same as the last digit of the powers of the last digits of each of the numbers in the sum, right? If I want the last digit of this number, I just need the last digit of 1 raised to n. Remember that property that we stated earlier. Now, if I want In the same sense, if I want the last digit of 1222, I just need to worry about the last digit of 2 raised to n. The last digit of 1333 is the same as the last digit of 3 raised to n. So I can replace, since all I'm interested in is the last digit, I can replace, I can, so modulo 10, the remainder, when this number is divided by 10, will simply be equal to this sum here. So if you want to estimate the minimum value of n, we test. Remember, we had been given some bounds for n. N would be between 1,000 and 1,100. So if 1,000 works, then our work is done. If 1,000 works here, then we would have found the minimum one. So if you set n is equal to 1,000, then you can write this as 1 raised to 1,000, which is just 1, 2 raised to 1,000, which is 4 times 250, 250, and so on. You keep going like that. And now, if you are considering this modulo 10, the remainder 2 raised to 4 will give you remainder 6 modulo 10, and 3 raised to 4 will give you remainder 1 modulo 10, and so on. 4 raised to 2 will give you remainder 6 modulo 10. We are just considering the remainder when divided by 10, right? And so the final remainder we can get by just finding the remainder when this sum 1 plus 6 plus 1 plus 6 is divided by 10. And this would be 6 plus 6 is 12 plus 1 is 14. So when divided by 10, the remainder is 4. I think that is a problem. We want remember, we want this to be divisible by 10. So if the remainder is 4, then we have a problem. It's not divisible by 10. So what's the next possible value of n? We can try 1,001 and see what happens. So using the same ideas, it turns out that the remainder when when n is 1,001, the remainder when this n is divided by 10 is actually 0. So I've not used anything new other than the ideas we worked with earlier. So since we are just multiplying by, raising this by, instead of 1,000, now we are raising by 1,000 plus 1. So if you consider this as n plus 1, it means simply multiplying. So if this was raised to 1,000, the remainder was 1 at 1,000. And it won't change when you go to 1,001. This one was raised to 1,000. And the remainder was 6, right? So the remainder was 6. And then to make it 1,001, you just need to multiply by 2 again to make this power 1,001. So you can multiply this by 2, right? We're using the properties of congruences. I don't know if I need to go back to them. I hope it makes sense. So using the same ideas, we do the same throughout. And when you add all this up, this is exactly 10. And therefore the remainder, when this number n is divided by 10, is 0. So this number n, when n is equal to 1,001, is divisible by 10. So the question was asking to find the smallest positive integer n between 1,000 and 1,100, such that this number is divisible by 10. So we found that if n is 1,000, it definitely doesn't work, right? So the next integer that we have to look at is 1,001. And since we are looking for the smallest, we can't get anything smaller than 1001 in this case, and that becomes our answer. I hope that makes sense.
Yes, yes, it does.
It does.
Yeah.
I don't know how we are doing on time. So the next question says, write down the last 4 digits of the number 7 raised to 128. So this one you have to break it down bit by bit, recursively. So we are interested in powers of 7. So we know that 7 raised to 4 is 2,401. If you work it out, that's what you should get. And when you consider it, since we are considering the last 4 digits, right? Remember the last k digits, then we have to find the remainder when divided by 10 raised to 4, right? So here the remainder is just 2,401. If you raise this to 8, so it means you raise both sides to 2, and you also raise this to 2. You don't lose the congruence. Remember the property that we looked at earlier? Here you don't lose the congruence. So when you raise both sides to 2, you end up with this. And you need the remainder when divided by 10 raised to 4. Now, if you expand this, what do you get? You use this expansion, a plus b squared is equal to a squared plus 2ab plus b squared. A squared plus 2ab plus b squared. That's what we are using here. So when you expand that and add, you are looking for the remainder when divided by 10 raised to 4. That is just the last 4 digits. So for this one, we will not worry because the last 4 digits will all be 0. We will not consider this one at all. But here, these ones are just 4,801. That will be the last 4 digits, because when you square this, the last 4 digits will be 0, 0, 0. And then when you add now 4,801, those will be the last 4 digits. And that's a remainder when divided by 10 raised to 4. Right? So again, we square this, we square both sides of this. If you square this and you square this side, you end up with this. 4,800 plus 1 squared, which is congruent to, now again, the same idea will work here. 4,800 squared will have the last 4 digits as 0. So the remaining terms are the ones that will determine the last 4 digits of our number. The remaining terms in this expansion. So we end up with this. We keep doing this until we finally reach our desired power, which is 7 raised to 128. And the remainder turns out to be 6,801 at that point when divided by 10 raised to 4. And that is, those are the last 4 digits that you're looking for. I hope that makes sense. Keep repeating the same idea until we are done to the end. But we have to be careful how we choose. 7 raised to 4 is a nice one to choose because you can split it into 2,400 plus 1. And anytime you square 2,400, it doesn't affect your last 4 digits. And therefore, you pick your last 4 digits from the remaining 2 terms of this expansion. So that's why, so this has to be done through trial and error. So if you, and then the good thing about 7 raised to 4, you can actually work with it until you get to 7 raised to. You can keep raising it to 2 until you reach 7 raised to 128. That is the strategy. Does that make sense?
Yeah.
Okay. So here is what we call the decimal representation of integers. It says let n be a whole number with the n plus 1 digits. Then it's possible to write n as follows. So it has all these n plus 1 digits. So you can write it as the first digit multiplied by 10 raised to n, and the second digit multiplied by 10 raised to n minus 1. These powers of 10 keep reducing as you move on until you reach the last term, which is just the constant term. Right. So this expansion is called the decimal representation of integers. So a simple example here is 2134 is the same as 2 times 10 raised to 3 plus 1 times 10 squared plus 3 times 10 plus 4, which is the constant term. So this illustrates this for a 4-digit number, but this can work for any number of digits. So I think this one is not too hard to visualize. So using those ideas, we can play around with the, sometimes you have questions that work with integers that have the same digits or repeated blocks of digits. So if you have a repeated block where it's all the same integer, it's an integer with all digits equal, and there are a total of n digits, then you can write it as let's use a small example so that you see what I mean. If you have 2, 2, 2, then you can write it as 2 multiplied by 1, 1, 1, right? So this 1, 1, 1 can be written as 10 squared plus 10 plus 1, right? So you can use the same idea for the general case where this is a repeated digit. You can pull out the digit and then express what is left inside the brackets here as sum of powers of 10, the same way I've done for 1, 1, 1. So if you consider this as a geometric progression or geometric series, so where the first term is 1 and the common ratio is 10, then the sum for this, usually the sum of a geometric progression is usually you multiply the first term by r raised to n minus 1, all of this divided by r minus 1. I think you're familiar with this, right? So for this geometric progression, maybe I should not use a because I've used a here. Probably I shouldn't use a here, but you get the point. So for this geometric progression in the brackets, or the geometric series in the brackets, the first term is 1, the common ratio is 10. So if you have 10n minus 1, that will be what is up here, divided by r minus 1, which is 9, then multiplied by what is out here, which is a. That's what it gives you. So you can simplify it like that using the sum of a geometric series, finite geometric series. So this works if all the digits are equal and there are a total of n digits. I'm about to run out of time, I think. I don't know whether this would be a good place to stop. Then we pick up from here next time. We have done more than an hour, almost an hour, I think. What do you suggest? Because we still have a lot to go. I don't see us finishing this within the next, this can be content for the next session. You can see it's still plenty.
I concur.
Yes, so we can pick up from this point.
I also concur.
Yes, we are in full agreement. So if you have any questions, we'll pick it up from here in the next session. I will stop the recording.